Distance measuring equipment, or DME, provides pilots with slant range distance from the aircraft to a ground-based station. The onboard DME interrogator sends out pulse pairs to the ground DME transponder, which replies with pulse pairs. The round-trip time is used to calculate distance in nautical miles. The DME operates in the L-band frequency range from 962 MHz to 1213 MHz in 1 MHz spacing. The aircraft interrogates on the receive frequency or interrogation frequency. Both of these terms are used interchangeably. The DME receives the interrogation pulse pair, processes the pair, and generates a reply on a different frequency that is 63 MHz higher or lower than the interrogation frequency. The reply is received by the aircraft and uses it to calculate the distance by measuring the time between the interrogation pulse pair and the reply pulse pair. The monitor receives the reply and uses it to measure various parameters to ensure that the DME is functioning properly. The aircraft interrogator is a multi-channel radio capable of transmitting on any one of the 126 channels in a frequency band from 1025 MHz to 1150 MHz. The ground station transponder is a single-channel radio which uses ground station to transmit distance information on one of the 126 channels in a frequency band from 962 MHz to 1213 MHz. This is a table showing the DME frequencies in X mode. Each mode has 126 channels separated into a low band and a high band. The low band is channels 17 through 63 and the high band is channels 64 through 126. Channels 1 through 16 are reserved for experimental use. The low band transmits 63 MHz lower than the received frequency, while the high band transmits 63 MHz higher than the received frequency. This table shows the Y mode frequencies for low and high band. Notice though that the low band transmits at 63 MHz higher than the received frequency and that the high band is now 63 MHz lower than the received frequency, which is the opposite to X mode. Now moving on to more DME general information. From the aircraft perspective, the aircraft transmits an omnidirectional interrogation. That interrogation reaches the ground station at the speed of light, where the ground station adds a 50 microsecond delay, and the reply to the aircraft is returned at the same speed. The aircraft calculates the distance by measuring the total travel time and subtracting the reply delay, then dividing by 12.36 microseconds per nautical mile. Distance measurements are the product of velocity and time. Since the speed of propagation of an electromagnetic wave in space equals the speed of light, measurement of distance is simply a measurement of time. Using the time-distance-velocity equation, we can establish that the range time for 1 nautical mile is t equals 12.36 microseconds, or the time it takes for a signal to travel 2 nautical miles. This is also commonly referred to as the radar mile. If the total number of interrogations does not generate enough replies to maintain the minimum transmitter rate, then the ground transponder generates pairs called Squitter at random times. Squitter is the number of random filler pulses generated to maintain an average transmitted output pulse rate of 1,350 pulse pairs per second. As more and more aircraft interrogations are decoded, fewer Squitter pulses will be required. And also it's important to note that the Squitter pulse rate of 1,350 pulse pairs per second could differ depending on the manufacturer of the DME system. The DME limits the number of replies to 2,700 pulse pair replies per second. More than that number causes an unacceptable level of coincidental interrogations and/or replies. So the DME can really only reply up to 100 airborne interrogators at a time. If too many aircraft are interrogating, requiring more than the 2,700 pulse pair replies per second from the ground station, then the receiver sensitivity will be reduced using an automatic gain reduction or AGR function. Replies will then be limited to the closest 100 interrogators. Another situation that affects replies is continuous wave RF levels. A faulty aircraft interrogator could potentially emit continuous wave RF that could jam the DME and prevent it from receiving interrogations. An automatic gain controller automatic gain reduction circuit in the ground-based DME system will determine the continuous wave RF level and automatically adjust to compensate. And in a sense, this will desensitize the receiver of the DME. Now moving on to the DME pulse characteristics. Every time the DME transmitter fires, for any reason, monitor reply, aircraft reply, Squitter identification, it transmits a pulse pair. These pulse shapes are Gaussian. The pulse rise time, fall time, and their width and spacing will remain constant. This diagram shows the X-mode general pulse characteristics. The pulse width is 3.5 microseconds. The pulse rise and fall time should be 2.5 microseconds in duration. The pulse spacing in X-mode is 12 microseconds. All pulse measurements are made at the 10, 50, and 90% points on the waveform. The interrogation and reply pulse pair in X mode are shown. The pulse spacing is 12 microseconds and a 50 microsecond reply delay is added. The tolerance for X mode reply delay is 49.4 to 50.6 microseconds. For the Y mode interrogation pulse pair, the interrogation pulse spacing is 36 microseconds. The pulse width, rise, and fall time are all the same as X mode. Here we can see that the Y mode reply pulse pair has a reply pulse spacing of 30 microseconds. On the Y channel transmitter delay, we see in this illustration that when comparing the first pulse of the interrogation to the first pulse of the reply, the overall reply delay is 56 microseconds. However, if we measure from second pulse to second pulse, we see that the delay is actually 50 microseconds. So the aircraft measures the second pulse to the second pulse when calculating distance for Y mode. This allows the 50 microsecond reply delay to remain constant no matter what mode is being used, X or Y. And lastly, here is a summary of the pulse coding for X and Y modes. Each ident group contains two pulse pairs, spaced 100 microseconds apart. The repetition rate of these ident groups is 1,350 pulse groups per second, which at intervals replace the normal Squitter and reply pulse pairs generated by the transponder. The 1350 pulse group signal is keyed by the DME keyer approximately every 30 seconds. These identity pulse groups formulate the dashes and dots of the International Morse Code Identification Signal. The dash is 0.3 seconds, while the dot is 0.1 seconds in duration. Let's now review the process that the aircraft uses to determine distance. Beginning with the search mode, the aircraft sends a series of pulse pairs to the ground transponder at a rate of about 120 to 150 pulse pairs per second. The ground station adds a reply delay and responds with the identical sequence of pulse pairs that it received. The aircraft then looks for the correct reply pattern with the correct interval using a stroboscopic process, and then switches to the track mode once it finds the correct reply, and uses a lower rate of 22 to 30 pulse pairs per second to maintain communication with the ground station. Of note, the stroboscopic effect could be understood when filming a rotating aircraft propeller blade with a camera. In that example, you can sometimes observe that if the frame rate of the camera is synced with the rotation of the propeller appears stationary. That phenomena is the same that allows the aircraft interrogator to distinguish valid replies from the aircraft or from other aircraft. Let's now look at two types of echo suppression, beginning with the short distance type echo. Echoes negatively can impact the distance measuring equipment. An echo is when an interrogation reflects off of an object and is received by the DME. If the echo overlaps the original, it could cause a reply, and this would cause an incorrect information to be received by the aircraft. So the DME is able to recognize this echo and suppress it. A long-distance echo is one that arrives much later than the original pulse. Both the interrogation and the echo could generate a reply, and this could cause the aircraft to break lock and lose distance information. So again, the receiver is able to recognize the long-distance type echo and suppress it. Let's next move on to the DME simplified transponder block diagram. Here we can see interrogations could potentially come from two sources, the aircraft or the monitor. Aircraft interrogations don't allow the monitor to measure reply delay because it doesn't know when the interrogation started. We basically really care about the monitor interrogations in this regard. The interrogation signal generator, or ISG in this example, generates the interrogations at the proper pulse spacing and amplitude to be sent to the monitor to start a timing process. The interrogation is injected into the directional coupler to take the same path as the aircraft interrogations. And here we can see the path of aircraft interrogations coming through the antenna, the low-pass filter, and the directional coupler. They then pass through a circulator in this example, while some DMEs could potentially use a transmit-receive switch or TR switch to route the signals to the receiver and transmit signals back to the antenna. A preselector narrows the band pass to plus and minus 5 MHz around the receive frequency. This filter usually has tunable cavities which allow for the frequency to be changed. And then the output of the preselector is fed into a mixer, with the other input being a continuous wave RF from the exciter. The continuous wave RF will be at the transmit frequency. The output of the mixer is 63 MHz pulse pair. The 63 MHz is fed into the receiver front end, and the front end processes the intermediate frequency, or IF, and provides two outputs, log video and on-channel video. The receiver then routes the on-channel and log video to the video processor for comparison. The on-channel video is used to generate enabling gates at the coincidental stage, and the log video is fed to the half-amplitude finder to produce the restored video pulses. Also, the log video is used to trigger the echo suppression circuitry when a predetermined amplitude level is reached. The valid interrogation pulses are then sent to the decoder circuit to begin the reply process. The decoder checks for the correct pulse spacing according to the mode, 12 microseconds or 36, depending on if it's X or Y. A pulse is sent out if the spacing is correct. The circuit also contains the Squitter generator, so if no distance pulses are present, Squitter pulses are output by that generator. A dead time gate is sent back to the video processor to disable the validation circuit to allow time for the reply pulses to be generated. The decoder pulse is sent to the encoder card. This card contains the encoder, priority circuits, and reply delay circuits. The priority circuit sets up the pulse generator priority, ident, distance, Squitter, and the delay circuits ensure the correct amount of time is added for the X or Y mode reply delay. The encoder triggers are sent to the pulse shaper to convert the triggers to Gaussian shaped pulses, and the Gaussian shaped pulses are then sent to the modulator. And lastly, the pulses modulate gated continuous wave RF from the exciter. The gated continuous wave RF is at the transmitter frequency. We now have a fully modulated pulse pair that will be routed to the circulator, where the reply pulse pair is routed then to the directional coupler and the antenna. Lastly, a probe picks off samples and sends them to the monitor for measurement. One sample, transmitted power, is sent to the monitor and measured for reply delay, pulse spacing, transmitter rate, reply efficiency, receiver sensitivity, power out, ident, and ident cycle time. Another sample, effective radiated power, or ERP, is sampled from the antenna radiated signal and is sent to the monitors for measurement as well. In summary, the intelligence of the distance measuring equipment is transmitted using pulse coding techniques. The transmissions are composed of pulse groups with a prearranged spacing between pulses of the group. The aircraft transmits a pulse group in the form of an interrogation. That interrogation is received by the DME ground station, and a reply is generated and transmitted to the aircraft. The aircraft measures the time from interrogation transmission to reception of reply to calculate distance.